Hello people, welcome to the next one. Today we're discussing delays, which is evidently a time-based process. Quite a lot to get to, so without further ado, as a matter of introduction, first of all, we encounter delay in space and matter. Because the sound has a finite speed. In fact, slightly slower than the fastest jet planes. And it is about a millionth of the speed of light. So quite considerable. Maybe you've noticed at a football pitch, you tend to see the ball being kicked first and then hear the impact. So as soon as the distance is sufficient, what you get is that in real world, in a physical environment, they mismatch the light and the sound. So the speed of sound actually depends on a few factors. It varies a little bit, around the 345, 340 meters per second. Depends on humidity, temperature, a bit of absolute pressure as well. Cool. So practically, we will look at many different effects, audio processes that necessitate delay, which is the main focus here. But it's worth noting that there are further uses as well. So typically in recording with multiple microphones, it may be that you want to compensate for the delay, okay? Because it's a fairly limited speed of sound in air. Therefore, it can be useful. We'll talk about interference, which may happen if you mix multiple microphone signals. Worth noting possibly is that the speed of sound in liquids is faster and in solids even faster. So air is kind of a slow medium for acoustics. A little sketch here for you. Different distances to the source will mean that the arrival time at these different sources will be different. We can consider this fairly self-evident. However, it is interesting to note that these arrival time differences are actually considerable, which might not be apparent from our daily interaction with sound. So let's take it to the digital domain already. There's quite something to be said about analog delay. In fact, what is dubbed an analog delay typically is a semi-digital process. It is a kind of a sampling thing, a bucket brigade delay in an analog circuit, which is technically a variable sample rate digitization. So the way this bucket brigade delay works is that you have an oscillator pretty much sampling the incoming signal, and then you have a different and then you have essentially a lot of buckets, right? So a lot of it's actually a series of condensers. I'm not sure if you're really interested in the electronics of it. I can push it before I start running out of time. But essentially what you have is a fixed number of samples or buckets, so to speak, where you can store voltage values. And therefore, the amount of delay is actually controlled by the sampling rate. So the frequency of the oscillator that moves the voltages onto the next bucket, so to speak, will control the delay time. So it is a kind of a digitization process, and in that it's a very inaccurate one most often. And there's huge issues with hearing the oscillator through as well. So typically a BBD, you would have to notch the frequency of the oscillator out, blah, blah. In any case, that's what they dub analog delay, I guess because it sells, but it's far from truly analog. The truly analog delay is actually a tape, where the transfer to the tape is analog and away from tape is analog. And that has been used historically in electronic music as the medium. There are certain funny things like oil can delay. So you can, although that's more of a modulation type effect because this oil can needs to be rotated. So indeed, you can come up with ways of slowing down the signal, but in essence, it's a really tricky thing to achieve because the density of information in the audio signal in relation to the amount of delay that we consider perceptually feasible is such that, you know, there is no medium where you can store all the detail, to put it in simple terms like that. So analog delay on the side, a bit of a transgression there. Let's go to the digital delay. So I guess you're becoming more and more familiar with samples. Although we don't directly see samples in PD, we definitely want to relate our understanding of digital audio to just plain numbers that represent different signal values. And what you often see is these simplified integers as well, just to make the point, which in this case is a fairly simple one. You see an A signal. Typically, if you have a signal and you like to refer to a single sample value, then you use the index and you put it in the brackets, often subscript, not necessarily. So you see that the 0th sample of A is 3, next one is 2, next one is 1. Similarly, thus a convention that the first element is the 0th one, so the index 0. And now if we delay this signal, we get the signal B, whereby the 10th sample is 3, 11th is 2, or I should say 11th, 12th, index 10, and so on. Not necessarily crucial, just a little display here. And also an introduction to having the time variable as the index here. So you see now the T in the lowest display, the T is your variable, so it could be any number. But what we do know is that the A sample will be 10 samples behind the B. So you can figure that out using the math. So with this variable, we are actually able to express delay times between signals without being specific about the actual samples. So it's a kind of a generic way of saying that it is 10 samples behind. Now, if we look at the basic thing that happens when we add delayed signals to themselves, to the undelayed original version, we quickly arrive to cancellation. So here is an example, again in a kind of a simplified digital display here. So if we have the sine wave, now in this case, maybe makes you a bit more familiar with what you may encounter otherwise. It's also useful, you can maybe use the grapher utility on the Mac, or find a kind of a mathematical graphing program where you can play with these equations. It gets quite interesting to me. But in any case, you might know that the sine wave has a period of 2 pi. And pi is 3.14, which means that once the value you take the sine of goes beyond 6.28, you actually get the sine wave to repeat. So that's the repetition point, so to speak, 2 pi. So what we have then is that if we take again the t, which is your time variable. And in a digital system, these are integers starting with 0, so the t will take on value 0, 1, 2, 3, and so on. If we multiply that by half pi, then what we get is that when t reaches 4, then we will have 2 pi, so that's when the sine will restart. Okay, so actually here the 0.5 is the value that allows you to control the frequency of this sine wave. Now in this case, you see, we are not dealing with the sample rate at all. We just have an integer time variable which increments by 1. So it is a kind of how should I put it? It's before we get to actually digital audio signals. We can already deal with sine waves, change their frequency in relation to the time variable, like this. Okay, so what this gives us, so you can see the E signal, it actually starts at 0, next value is 1, back to 0, and then -1. And that's a full period, and then the whole thing starts all over again. So this was the trick to make a little very simple sine wave-like signal, although it's a bit more like a triangle, as you may imagine. And now we can verify that if we delay this signal by 2 samples, we get the F signal. And if you actually add up every number of the E signal to every number of the F signal, you get a 0 signal. Every +1 will line up with a -1 and vice versa. All the zeros line up as well. So E plus F is just a bunch of zeros. So essentially what we've done there is we've cancelled out the original signal by adding to it its delayed version. Okay, excuse Eric, I kind of missed removing that. These signals were called Eric and something with F before I intervened. Who knows? Who knows? If you're interested why I feel aversion to calling signal names, I can let you know. In fact, it's a bit of a, it seems to make it simpler, but it doesn't, to call a signal Eric. The only thing it does, it makes you feel maybe a bit simple, or makes you feel that things are simplified where they shouldn't be. So in any case, for every sinusoid, every sinusoidal signal, there should be a delay. There is a delay which will cancel out the signal, may you add it to its delayed version, which actually also means that every complex signal, right, if you delay it and add it back to itself, will have some frequencies cancelled out. Okay, now which frequencies are cancelled out? Well, you can figure it out here. In essence, the delay, when the delay matches half of the period duration, then those frequencies that relate to that period duration will cancel out. So we can play a little quiz here. What amount of delay would cancel a sine at 1 Hertz? Okay, so the answer there is that we need to delay it by half the period. So 1 Hertz has a period of 1 second. So if we delay it by half a second, it will cancel itself out. And what needs to happen on top of delaying the signal, never forget, delaying is insufficient. You have to add it back to the original. In fact, delay is an evasive thing. You can't really notice the delay unless you have a reference. That's why when someone talks to you, you don't notice the delay, because it's the first and the only signal that arrives to you, like that. where there is technically a delay between the voice production and the perception of it. So very importantly, if delay is supposed to be audible, there has to be a reference to the delayed signal as well. Okay, so it should be clear. Takes time to go through space. Another word we might use is to postpone a signal, postpone samples of a digital signal. Sometimes it is important to note that delay is used as a name for an effect, which is typically a feedback delay. It's kind of an echo thing, right? Just to avoid confusion, postponing samples might be a bit narrower in terms of description, such that you don't think of the delay pedal or a VST, which is called delay. But I assume in this context, you understand that we are dealing with a very bare bones delay, postponement of signals. So the shortest delay amount in a digital signal will be a single sample delay, which is the building block for basic filters. We will study this, but just to mention it ahead. And if it is not a single sample delay, which essentially needs one memory cell just to remember what was the previous value until the next one comes in. If it's more than that, if it's more than just one sample delay, typically what we use is a buffer, which is a larger amount of memory that is allocated to store multiple previous samples. And here we will introduce the solution that makes this efficient, which is called a circular buffer. We'll talk about this in a second. There could be improvements to what you imagine is a basic delay, where you can postpone samples by integer multiples of a sample duration. We can actually have something that people might call fractional delay or an interpolating delay line, which allows you to postpone the signal by 2.6 samples. And in which case, what you need to do is you need to calculate what would the sample value be at 60% between two samples. So there's a kind of an interpolation happening there. And that will allow us to have a higher precision of delay times, as you will see will be necessary when we tune resonators like Karplus Strong and such. So if we work towards understanding the circular buffer, first step is to understand that if we have an amount of allocated memory and a new sample comes in, we would like to avoid shifting each and every sample on. So avoid doing an actual bucket brigade action where in every step the whole signal has to move, which is a lot of reading and writing for the memory. So instead of doing that, what we do is we progressively write into the buffer, as you see it here. And this we call incrementing the write pointer. So essentially, the write pointer is a variable which specifies at which point in memory would we need to write the sample. And once it's done, it increments by 1. So the next time around, we will be writing to the next memory cell. And then evidently you run out. And then what will happen is that a circular arrangement, well, evidently you're not rearranging memory chips, but a circular pointer, to be very precise, will come to our help. So in looking at the buffers, writing is fairly evident in terms of incrementing the writing pointer. And a similar thing happens with reading pointers. So again, a value that specifies the location is being incremented. And this operation is what we also call indexing into the array, indexing into the buffer. The term buffer itself specifies a certain amount of memory available. And you might have encountered it also in analog to digital conversion, whereby you can potentially change the buffer size, typically called the hardware buffer size. It has to do with nitty-gritty bits of electronic engineering. How can you transfer digital signals more efficiently? And typically what you will have is a different buffer size, potentially, for the processing using the CPU, central processing unit. So these are typically two separate buffer sizes, could be. So once you have the digital signal in your software, it actually takes a lot of CPU to set up a calculation, more so than execute it. So that's why, for efficiency, we would typically run the audio in larger chunks. So we have to set up a process once and we can run many samples through it before the next process needs setting up. So typically if your CPU is struggling, increasing the block size, which is our software buffer, may reduce the CPU demand there. In terms of hardware buffer size, increase and decrease, typically what you're dealing with is changing latency of the system. So a smaller hardware buffer size means that before the sample incoming signal recurs at the output, there is less delay because you need to fill in a smaller buffer. Obviously, fill it in, process it, send it out. It all takes some time. So decreasing hardware buffer size will decrease your latency, which may be crucial if you have a live thing happening between input and output. If you don't, if it's just synthesizing sound from the machine, playing back recorded sound, then typically this is unnoticeable, the amount of delay latency that happens. Again, also because there is no reference. Obviously, if I press play, my ability to discern between 10 and 100 milliseconds of delay is not great unless it's a percussive interface and I'm a percussionist. Okay, so other than these basic buffers, what you will find is that they're used in many different effects, delay-based effects. We will summarize these by the end of the class. And we will talk about filtering, comp filtering in further sessions. So that will be coming. And just to try and complete the list here, typically you will encounter the term buffer in spectral analysis. If you're trying to analyze the spectrum of a signal, the frequency contents, typically using fast Fourier transform. And there this buffer actually has another added function because it will control the resolution of your spectral analysis. So if you have a small buffer for your spectral analysis, what you get is good time resolution because they come in quick succession and you can pinpoint where things happen. Now, if you have a large buffer, then your time resolution may suffer, but you get an increased frequency resolution, so you have more data to work with to analyze. And then finally, in granulation type processes, we'll get to that as well at some stage. So it just goes to show that pretty much everything will need some kind of buffering or delay. The one thing which evidently doesn't is the nonlinearities, right? So they're also sometimes called these memoryless processes. Whatever comes in comes out straight in an altered fashion. But you will find that an increasing number of audio processes actually needs some delay even when you wouldn't expect it. Like basic filtering is all based on delays. Okay, so reading and writing, incrementing the pointer, I guess that should be straightforward. And then the final step to understand the circular buffer here is to essentially wrap it around. So once you come to the end of your memory, you wrap it around and the next slot becomes the first slot. So the last slot links up with the first one. And then you can infinitely keep incrementing the read pointer and also the write pointer. So what you can imagine is then the read and the write pointer kind of chasing each other along this circle. And if the distance is fixed, then you have a fixed delay time, right? Because every time one head moves, one pointer moves, the other one moves as well. And if the distance is a fixed value, then it means that it'll always take the same amount of time for the read pointer to read what was written a second ago or some time ago. And then you can also imagine that if the distance between the read position and the write position keeps changing, then you're essentially changing the delay time. And you can also mimic a constant increase in delay time or decrease in delay time by having them run at a different speed. And once you understand that, it will make sense why you will get discontinuities, because if they run at a different speed, they will cross each other, at which case the signal that is being output is discontinuous, causes clicks and pops. Also in terms of the smoothness of changing delay time, if it's not a smooth change, then you might get clicks and pops as well. So essentially delay lines are fairly sensitive like that, and you've seen us use it as a vibrato effect already. So it is crucial that increasing the delay time by a constant increment will cause a pitch shift. Okay, it will pitch shift down. Okay, so that's your circular buffer. I mean, it's not horribly pertinent to using delays or building complex effects from delays, but it's a good insight in terms of what's actually going on in your signal processing code or underneath your signal processing objects, because all of this is taken care of for us. So one thing is to dig a bit deeper, and the other thing is to understand why are there pops and clicks and when do they occur, because you would want to avoid them typically. Okay, and the other thing that it shows you is why it is necessary to specify the maximum delay time, which is something that you are encountering already likely, because you cannot make this circular arrangement. I mean, it's not a circular arrangement. You can not make this pointer circular easily. Although you could dynamically update this, probably the bigger issue is that the operating systems have an asynchronous memory allocation, which means that you can't count on it being ready by any time. When it's ready, you get a report, to simplify matters here. But in any case, it is a matter of fact that we need to figure out what the maximum delay time is before we get to use the delay line. So the question arises, how do we wrap things around? Depends on the environment it's coded in. You can have an if-then type clause. So if the pointer runs over the limit, then subtract the size of the buffer from that pointer. So once it reaches the maximum, it goes back to 0. But actually, it's probably useful to introduce the modulo operation, which uses this percentage sign, but has nothing to do with percentage. It's kind of a mathematical operation, which has this wrapping behavior. Oops, that slide is slightly misplaced. So this is the modulo. directly taken from a mathematical graphing application. So the equation there is y equals x modulo 2. And what modulo is, I mean, it gives you a kind of a sawtooth wave, a phasor. And what it does, it actually gives you the remainder of division, the remainder of integer division. So it's the kind of division you might remember of before you studied decimal numbers. So if I have undivisible objects like cash bills, right? If I want to split a 10-pound bill in two, I cannot quite cut it, or in three. It's indivisible like that. Obviously, you can break it down, but that's different. So what you do then is you divide equally as much as you can, and then you call a remainder, right? Or what else can't we divide? Bloody hell. Well, we can't divide symbols. You can't see it. I have quite a lot here next to me. So if I have 5 symbols and I have to equally divide them among 3 people, then the only fair thing to do is to give everyone 1 symbol and have 2 remaining. So that's your integer division like that. And then if you do a modulo, you're actually looking at the remainder only. So you don't care about how many symbols everyone gets. I'm kind of liking this metaphor now. The only thing I care is about how much I have left, once I've divided them equally. And this becomes a cyclic function, right? So if I have 5 modulo 3, the result is 2. I have 2 remainder. But if I have 6, well, then everyone gets 2. There is 0 remainder. So see, you get a cyclic function. Well, here you're looking at modulo 2, right? So I'm dividing a number of symbols between 2 people and looking at the remainder. So if there is 0, there is 0 left. That's evident. If there is 1, the 1 will be left. I cannot divide it. If there are 2, well, then what you get is that the remainder is back to 0 because I managed to divide them equally. And then if it's 4, again 0, 5, 1, and so on and so forth. So in any case, it's a useful trick potentially in your signal processing, especially because the if-then type operations are not always available in real-time signal processing environments. In PD, you can actually do expression tilde, and you can do some if statements in audio at audio rate. But typically, as far as the actual compilation of those processes go, they will end up running all the signals. You can't quite stop a signal like that, or kind of run it or run it not. Okay, so we jumped over one thing which said bits about this in PD. You've seen these objects already. The thing to add probably is that VD is different from del read in that it allows you to specify the delay time as a signal. So if you want to really have a detailed control over delay time changing every sample, then you need a VD, or indeed if you're just using signals for it. Otherwise, del read will do the trick. And then what you've seen in PD as well is that you actually get 2 objects which address the same memory space, which is named after Robert in this example. And what you've seen also is that they don't connect by patch cords. And now that you hopefully understand everything about circular buffers, you understand that there is a read pointer and a write pointer, and they don't necessarily need to talk to each other either. The only thing they need to do is address the same memory space. So hopefully now it makes sense why these objects are not necessarily connected. Even though, I mean, the reason is evidently you might say, well, why don't you make it in a single object and it will be more intuitive? It would be. The only difference is that if you do it in a modular way like this, so you have a separate buffer, you have a writing and you have a reading object separately, then you may add multiple reading objects and have what we call a multitab delay, or you can do something unexpected with multiple writing points. Probably going to be very glitchy, but that could be your objective. So evidently we will deal with the practice more in the workshops. I believe I have explained everything about circular buffers, so may this serve as a reference. If you're interested in doing some calculation here, I won't spend more time on this, really want to get to the more practical bits. But if you have some motivation to calculate around things, or indeed at least to have a sense of what could be calculated, that's worth quite a lot actually, then you might want to spend some time figuring these bits out and then do a bit of homework as well. I leave you to it. Evidently, if you've attempted it or get stuck, please address me in the workshop and then we will discuss it. Okay, so let's look into this cancellation in a bit more detail, because it is not like it's either cancelled or not cancelled. There could be many things in between. So in any case, summing delayed signals to the original ones will cause interference. And depending on the delay time, or more accurately, depending on the phase shift, you will get a different result. So what we have here is the first column gives you out of phase signal, 180 degrees phase shift or a pi phase shift, and you get total cancellation. In the second column, you see that the offset, the phase offset, is a full period, and therefore we get constructive interference, as we call it. So the gain is increased, the signals reinforce each other. And then what we get is doubling the frequency. Sorry, I'm saying this wrong. Does it say somewhere what has happened? Because it's not exactly double the frequency, it is 3 times the frequency. In fact, I'm playing this slightly wrong, okay? Erase that from your head. Let's go again. So in each column, you have an increasing frequency. The delay time is the same. And then we are looking at what is the result, right? So if the frequency period is half the delay, right? We've said this already, we get cancellation. That's your first column. Now in the second column, we've doubled the frequency. So actually the same amount of delay will give you a constructive interference. And moving on, again, the same amount of delay at 3 times the frequency, it will again give you destructive interference, cancelling out. At 4 times the frequency, again, reinforcement, 5 times the frequency, again, cancelling out. And this series continues like that. So what you then understand is that if you add a signal to itself after delaying it by a fixed delay amount, you will get a periodic repetition of cancellations and reinforcements, which is actually your comp filter. Okay, so we will get to that. In fact, we will discuss comp filtering in more detail when we get to filtering. But it's a useful term to have in the back of your mind in relation to adding delayed signals to themselves. Okay, so that's the explanation here. The crucial thing to understand then is the difference between a phase shift and the delay. Well, first of all, the phase shift makes sense as a term in relation to periodic signals. If your signal is noisy, it is difficult to consider them having a circular phase like that. So we rather talk about delaying non-periodic signals. Now, if it is a periodic signal, it means that it repeats. Then the term phase is crucial because it allows us to understand how the processes that we might use will depend on this circular property of the signal. So typically, therefore, the basic signal we deal with is the sine wave. Now, what is the difference between a phase shift of a sine wave and a delay of the sine wave? Well, both are delays, really, technically. The difference is how they're expressed. Okay, so delay is evidently something we express using seconds, milliseconds, time units. And phase is something we express using degrees or radians, which relate to the cyclic nature of the signal. So the point is that the same amount of phase shift will be a different time delay for different frequencies. Okay, so if you say, well, simplest case, if my phase shift is 2 pi or 360 degrees, a full period, evidently if my period duration is 1 second, the delay will be 1 second. If my period duration is a tenth, then the delay will be the tenth of the second. So the phase shift kind of carries in it the frequency information as well, so to speak. Okay, so might be slightly tricky to wrap your head around this, but these terms and the meaning should fall in place as we progress with the practical bits as well. So let's get a bit more practical here. I think we have the basic background sorted, and see about the usage of delays in this context. So first of all, what we have is the ability to model, mimic what happens with all the reflections and sound waves traveling around us, different distances of objects, distances between receivers and emitters, all those things. In fact, one of the basic properties of enclosed spaces is that they're very rich in reflections. So we can potentially mimic or model what happens in a room using a whole lot of delays. Now, if you think about this, you probably realize that it's way too complex, in the sense that, first of all, do we model the sound propagation using arrows? Is a good question. We can also model it using concentric circles. I won't go into this distinction here, but if we are using arrows, which would kind of help us think of distances and similar, then what you get is the question, well, how many arrows, right? So if I have a point source which is radiating in 3 dimensions spherically, how many arrows do I need to describe this? It's a good question. The answer is, well, depends on your CPU. These techniques are called ray tracing models, by the way, and some of the acoustic modeling software uses that. But in any case, it has to be a limited resolution in that. So even the most simple room can only be approximated in this sense. Now, nevertheless, we can mimic the generic behavior of things, the generic properties of reverb, reverberation of enclosed spaces. By the way, open spaces reverberate as well as soon as you have a reflection, right? Just go clapping in the woods, especially if you're in between the hills in valleys and stuff, right? Valleys have a lot of reflective surfaces. So the point is that, with multiple delays, we can start coming close to something like a reverb. However, reverberation as such is a very complex topic. It was the holy grail of signal processing for decades. You had certain analog solutions like plate reverbs and spring reverbs, oil can delay for that matter. But in digital domain, to computationally approximate this was quite a challenge. And is to this very day. In fact, the kind of reverbs that we consider natural are typically based on analyzing rather than modeling. Okay, so you analyze existing spaces rather than model. I'll probably say a few things about reverb here and there because it relates. Seems we have no scope to really dig into it, and these processes become increasingly complex as well. A bit left for filtering once we get into comp filters. We will see how they can actually come close to give you some sort of reverberation. Okay, so what we're looking at then is essentially multiple delays stuck together. We call this a multitab delay. And it can be useful. Here is a sketch, multiple delays, filters. You can throw up as many as you like, really. The thing is that these schemes will initially sound terrible. I mean, unless that's the desired characteristic. Because you will get a lot of notches, a lot of resonances. It can be quite unpleasant sounding, this kind of early reverberation, again, unless that is the point. We won't go very far into this, but briefly instead discuss the analytical side of producing a reverb, which has everything to do with measuring an impulse response. So rather than figuring out what would be the distances to all the reflective surfaces, you just measure that. So theoretically, you can understand this in the terms of emitting an impulse and then recording everything that happens after that impulse, all the reflections of that impulse, which come slightly later. So you actually get a graph like the one you see, where each reflection is happening further down the line in time, and each reflection is typically softer, or as a whole they are progressively softer. Evidently it depends on the surface. The interesting thing about the real world rooms is that you have an increasing density of reflections. So once they start arriving, they really get to it, and by the time you're into the reverberant tail, the density of these repeated impulses is huge, and that's what makes a lush reverb, among other things, which is something that very simple analytic models don't have. So they would have a given density of reflections that typically die off. That's easy, reduce amplitude, but they wouldn't have an increasing amount, which is quite crucial. So this impulse response is quite useful. You can measure rooms with it. And in fact, linear systems are well described using impulse responses. So filters, I mean, you can describe a gain stage using an impulse response. I mean, it won't have any reflections, but the very impulse will potentially have a different magnitude, and that then describes your gain stage. Evidently, just to wrap that in, nonlinear processes like distortions, right? Like you cannot express them with an impulse response. Okay, because the gain, right, the level of the impulse response, evidently there's nothing in terms of reflections, but the gain is actually not linearly related to the input gain, right? So if it's too loud, then you get this kind of compressing thing on top. If it's too soft, it's fairly linear, and you cannot express this with an impulse response. So for nonlinearities, that's why we use transfer functions. Okay, so I think I'll leave most of the reverb stuff for after filters, once we have a few more building elements sorted. So I'll probably transfer those slides as well. Okay, so multitab delay is the term I've mentioned already. sometimes you will encounter the term delay network. Tap point is your reading pointer, really. So having multiple reads from a same buffer will be your multitab delay. Sometimes you will find a scheme where you actually have multiple delay boxes, like the one on top right here, which might suggest that they are different buffers. So it will be up to you to figure out, well, do I actually need to write into separate buffers in order to get this done? And if they share the same input, these delay lines, then you could get away with a single buffer. So might be a good idea to optimize along those lines. And then once you have this system with one input and multiple outputs, and you want to get wild, well, a lot of feedback can do interesting things. So we'll talk about that. Okay, now briefly about modulating the delay time. So what happens if you change the delay time as the signal plays? It is something that you've heard already, relates to Doppler effect, right? So again, we are back to this match between delay and propagation in air or materials otherwise. So what you have thus in an acoustic environment is if the source, the sound source, is moving in relation to the receiver, then the pitch that is being received will differ from the emitted pitch. Okay, so that's your car passing by sound, right? So when it's approaching the receiver, the pitch is shifted up. When it's departing from the receiver, the pitch is shifted down. And this is a property of acoustic environment. So it is just, well, that if you change the delay time accordingly, so if you keep decreasing the delay time, meaning that a sound source, or matching the situation when the sound source is approaching, then you will get a pitch shift up. And if you keep decreasing the delay time, increasing the delay time, did I say it well? So if you increase the delay time, it's like something departing from you, the distance is increasing, the duration of time it takes for the sound to come to the receiver is increasing as well. In this case, the pitch is lowered. Okay, so that's why you have the situation when you modulate the delay time with the sine wave, right, going up and down, you actually get a pitch shift going up and down. Okay, so we get a vibrato type effect. And then the thing to remember is that this is the effect of just delaying the signal. But if you add the original one to this modulated delay signal, then you actually get a slightly different effect. Evidently, it depends on the delay time range as well. But typically, instead of just the pitch shifting vibrato type effect, you get a fairly strong filtering effect as well. Flanging or phasing are the terms that cover that typically. Okay, so let's look at a few more basic structures here. I mean, these are useful for you to practice also in terms of implementing into PD. I hope they are fairly transparent like that. And what we see here is a feedback path. Okay, so in order to produce a feedback, what you need to add the signal back to itself after being delayed. So actually a feed-forward delay and a feedback delay will be crucially different, because in a feedback structure you will get the reflection to repeat. If there is no reduction of gain in the feedback loop, it will actually repeat forever. Whereas if it's a feed-forward structure, then you just get a single repetition. Okay, so this will be useful, again, to simulate essentially your standing waves potentially when you get this bouncing between two surfaces. A quiz. Okay, pause there and think of the answer and bring it onto the workshop. I will accelerate a bit just not to run out of time. So here is a flanging effect scheme. And what you see is a delay line in a feed-forward structure. So the bottom of the graph, the delay and the summer, are your audio chain. So input, delay, sum to the original output, that's your audio chain. And then everything on top is actually your control chain, where you have a modulator. This looks like a triangle wave at this stage. You have a dial to control the frequency of the triangle wave. And then you have scaling and offsetting, right? So scaling, multiplying this modulation signal will cause it to grow or shrink, which is something we call modulation depth. And then offsetting it will actually control, in this case, what is the time offset for this signal. Okay, there could be differences. It's not a hugely responsive dial, the offset. That's why in this case there is only one dial which does both depth and offset. So if you think about this, if I multiply with the same number as the number I add to, then I will get a unipolar signal from a bipolar signal, right? So if I have a -1 to +1 original modulator, which is typically the case, then what you would get is, let's say, multiply with 5 and +5. So if I multiply with 5, it's going to be -5 to +5. +5 will be 0 to 10. And if you pick number 35 or 36, the same thing will hold. You will get -36 to +36, add 36, you get 0 to 72. So in that's a useful trick. You just add and multiply using the same number, and from a bipolar signal you will get a unipolar. And in this case it's fairly useful because you cannot run a negative delay time. That would be seeing the future. Okay, and then to wrap it all up, here is a table of many different standard effects that have delays at their cores. And you can kind of compare them, see whether they have a modulation embedded or not. Some of them will, some of them won't. And most importantly, you see how the different delay times will mess with different perceptual characteristics. So the shortest delay times will actually mess with the spectrum. Typically filters will be effects that use the shortest delay times. Midway, what you will get is that you are changing the spatial characteristic of signals, typically reverberators, chorusing to an extent. And then what you get if the delay times are really long, so those effects actually affect the musical, the actual perception of time, right? So once the delay is sufficiently long, you will hear the repetition. If it's very short, it's just a filter. If it's medium length, it messes up the spatial characteristics, size of the room or similar. And then if it's really long, you actually hear it as a separate musical event. So in any case, many effects there for you to explore. What we're trying to establish is a good foundation that allows you to really go your own way in exploring and implementing these things, hopefully developing your own interesting and experimental audio processing in the next semester as well. So thank you for your attention, and I will see you all very shortly.